Start the afternoon session. Please join in the line.
Okay. Ready? Go back to the first slide.
Right on the
Yeah, I think we got the first slide. Yeah, the previous one. Yes. This is good. This is good. Okay. All right. Welcome back. Good afternoon. We're going to continue on the theme of anaerobic digestion. We're going to be talking about, common term biogas, and we want to use what else we can use other than methane, value added product like fatty acids and other things using anaerobic digestion process. Okay. So some of the slides may be redundant. We are repeating little more, but in more details, I'm going to give you more bacterial name, more enzymes, and all that. But whatever you can take it. Okay. But it's too much, ignore it. But you're going to have the slides with you. I'm going to give you all the slides. You can use the slides for future reference. Okay. So it's going to be on biogas fundamentals and alternative products from anaerobic digestion. I prepare these slides with my best friend, Dr. Mohammed Tagarzadi of University of Borås in Sweden, and he is my collaborator. What is biogas? Basically is a gas come out of anaerobic process. In nature, it's in all the ruminant animals, like the animals that can eat the lignocellulosic, and then they ruminate. That means they chew the cud. They have 4 chambers in the stomach. They eat as fast as they can, and then when they rest, they regurgitate and then chew it back, and each of the chamber act like anaerobic digester. So that's one of the best example is cow, right? So cow produce a lot of methane gas. Okay. So this is another reference book. If you are interested, you can check that out, or all the anaerobic digestion renewable resources available. So when you look at landfill is like a solid anaerobic digestion process. Okay, so what they do in the Western countries, and they call it sanitary landfill. They compact the waste every day so they don't pile it up. And then after 5 years of landfill into service, they put gas collection system. And everything we talked about in the morning about anaerobic digestion is what's happening in the landfill. Okay, so when you compact it, you create anaerobic conditions, and then after 5 years, you recover methane gas from a landfill. Okay, so it's very common practice in Western world in sanitary landfill. That's what they do. Okay, that's how a methane recovery system look like in a landfill. They have a gas collection pipes all around, and you can have in a decent sized landfill, you can collect 40,000 cubic meter of gas per hour in a landfill, and then they have to purify the gas and make it to 98-99% of methane in the gas, and then goes to compressed gas system or natural gas pipeline. They sell it as a product. Okay, so this is a best way of closing the loop. So gas is not going up into the atmosphere causing greenhouse gas. You are collecting the gas and using the gas. So again, it's an anaerobic digestion concept. It's a solid, high solid anaerobic digestion. Okay, so that's what they do in landfill. They collect the methane, purify the methane, and sell it. Okay. Oops. So greenhouse gas effect we talked about. So the variety of gas they produce in anaerobic digestion are listed here: methane, carbon dioxide, nitrous oxide. Depending on substrate, you may produce a lot of fluorocarbons. Depending on sulfide, ammonia gas, and all that. So if you take CO2 as one unit causing greenhouse gas, methane is worst. Methane is 21 times more worse than CO2. And if you look at the gas that you produce, nitrous oxide is even worse. So as the list goes on, so when we talk about greenhouse gas, only talk about CO2, but there are worse gas other than CO2 that goes. Methane is 21 times worse than CO2. Okay, and nitrous oxide is another major one. So these are the gas that wastewater treatment system we produce that if you don't capture them, you're contributing to greenhouse gas. Okay. So this is the overall view of the picture of not only you're producing methane, you're producing digestate, we're producing other gas. This is the overall scheme of what's happening in a digester, in an anaerobic digester. Okay. It's going back to. So the biogas component. So we talked about little more in the morning here. We talked about a little more details. We have how much CO2, hydrogen sulfide, ammonia are produced, and what effect it has on the whole system itself. Okay, so you have nitrous oxide emission has a problem, and you have CO2 has a lower calorific value when you have mixed with biogas with methane. Hydrogen sulfide is a corrosive effect. So all those are combination of various gas you produce in a digester. Okay, if you have a lot of those silicon, you can produce the silicon related gas. That's also a problem in anaerobic digester. So general facts about biogas: the composition varies based on your substrate. So the major ones are methane and CO2 and other trace gases. So energy content is 6 to 6.5 kilowatt hour. Fuel equivalent of 0.6 to 0.65 liter of oil per cubic meter of biogas. You can compare metrics, how valuable the biogas is. Explosion limits is listed here: ignition temperature, critical pressure of methane, critical temperature, normal density, and it smells. If you have H2S, it smells like bad rotten egg smell. And then molar mass is 16. Methane molar mass is 16 molar mass. So some property of biogas. So depending on the substrate, whether it's a C1 compound, C2 compound, all the way C6 aromatic compounds, what is going in there, your methane composition increases. The more carbon chain you have, higher methane percentage you have in your gas. So if you look at the average methane is around 50%, but if you have formic acid is only one carbon, and if you have acetic acid and other acid, you have low methane component. If your substrate has like a benzene, benzoate aromatic compound, you are producing more methane gas. The more carbon you have, more methane is in your end product. Like your long chain fatty acid, when it digested, you get more methane gas. So the input, what is going in, how much carbon in there, make a difference is how much methane composition in your digester. So I don't want to bore you with too much biochemical reaction. So if you look at this stoichiometry reaction and how much water is needed to break it down, you get, if you compute that into your equation, I've just simplified it for you: carbohydrate, fat, protein. So from one carbohydrate, you can make 3 CO2 and 3 methane. Okay? From one fat molecule, you can make 4.5 carbon dioxide, 7.5 methane gas. From one fat. From one protein, you can make 6.5 CO2, 6.5 methane, 3 ammonia, and hydrogen sulfide. So depending on what is in your feedstock, your percentage of methane varies because number of carbon in your organic carbon that goes in makes the ultimate end point of what you're producing. So this is simple biochemistry of what is in your feedstock, and that produce different composition of gas. Oh, okay. It's okay? Yeah. Okay. So, it's a simple stoichiometry of your feedstock makes a difference in the composition of your gas. Okay. It's not working here. Want to click on this? Is it going to work? No. It's not forwarding. Okay. Let me see. It's going to forward. Yeah, it's forwarding. All right. So let's look at substrate for biogas production. You can use liquid manure, bio waste from municipal solid waste, agriculture waste, landfill, sewage sludge, industrial wastewater, energy crop, algae, plankton, other sea sediments. Anything that has rich in carbon could be used potentially as a substrate for your digester. Okay, so you can look at the lignocellulosic basically from agriculture feedstock. You can put that in the form of called co-digestion. You mix with manure and you digest the feedstock, agriculture feedstock. So important factors of formation of your biogas is the dry matter content of the material, water content, also organic matter, how much organic matter in your feedstock, degradability of your substrate, salt content. In the morning we talked about nitrogen phosphorus ratio, trace element, granulation, presence of heavy metal also affect, and then content of your short chain fatty acid, example acetic propionic butyric acid. Okay, and then CN ratio, general rule of thumb you have to follow, how much carbon, how much nitrogen you have to have. Okay, so let's look at overall picture. In photosynthesis, what happens, we take carbon dioxide with water. In the presence of sunlight, we're converting carbon dioxide to carbohydrate. So that's, we're fixing energy in photosynthesis. In anaerobic digestion, we are breaking it. We are losing energy, breaking the carbohydrate and releasing methane. So that's what's simply happening when compared photosynthesis in anaerobic digestion. So what is remaining is your methane and carbon dioxide in the process. Okay. So this we went through this morning. Again, go back one more time. These are the biochemical reaction that's happening inside the anaerobic digesters. These are different reaction we already went through. Okay, so that's where organic matter is broken down to biogas. So let's look at a little bit detail. So if you have protein in your substrate, for example, restaurant waste or food industry waste, rich in protein. So what you have protein is basically amino acid. That's how amino acid looks like. It has a amino terminal and carboxyl terminal. And when you put them together, you make a protein in a peptide bond. And then you have cellulose and hemicellulose. You can break it down to make sugar. And you have fat-rich compound that can break it down to fatty acid and glycerol. So these are the list of bacteria that are everything that we know of in the digester is listed here, and what each bacteria does is also given here. Okay, the first one is basically mostly Clostridium bacteria, what it does in hydrolysis, and propionic bacteria, all that is listed here, and it's too small to read, but I put in all the information in the slide, so you could use it later on after the talk, okay, when you get your slide. So in acidogenic phase, what's happening is all this product of fatty acid with the structure given in there, and the bacteria is producing these acid from breaking down your complex carbohydrate, complex protein and lipid, and they end up making fatty acid like propionic acid, butyric acid, and that's what in the acidogenetic phase is happening. All the acid that can make in the digester are listed here, everything with biochemical structure. Okay, so more details than what I presented this morning. Again, acidogenic genera, the common one is Clostridium. All the Clostridium species are listed in there. What each species preferred substrate is listed in there. If you look at the first one, they like cellulose. If you look at the second one, that look xylone, xylosic sugar. So every organism that we know in the digester we already classified, and we know exactly what substrate they prefer. Okay, so more information than you need, but that information is out there for you to use. Okay. In acidogenic genera, the Ruminococcus genus is the one that dominate, and I have all the species listed here, and the preferred substrates also listed here. Okay, they are generally anaerobic bacteria, and they look in a round shape. They call cocci, and they ferment carbohydrate to acetate, formate, succinate, lactate, everything I given in the previous slide. That's what they make. And then another group is called Panibacillus genus, and Panibacillus genus produces lactic acid, acetic acid, propionic acid. So all the bacterial names and what they do are listed here. Then the acidogenic phase is the bacteria that convert propionic, butyric, valeric acid to acetic acid. Okay, and those are the chemical reaction of all the acid you can produce, including ethanol during your hydrolytic phase, an acidogenic phase, and then the reaction involved in breaking down each of those acids to make acetic acid. What's happening biochemically, the end product you get in acetogenesis is acetic acid and hydrogen and a little bit of CO2. Okay, so every acid you produce is finally converted to acetic acid. That phase is called acetogenesis, production of acetic acid. Okay, and then you have carbon dioxide and hydrogen is produced. Then bacteria can use those, and these are called autotrophic bacteria, not heterotrophic bacteria. They can convert them to acetic acid as well. Okay, and then finally the sulfate reducing bacteria that plays a key role in producing acetate, but at the same time too much of sulfate reducing bacteria going to compete and going to hinder methane production. This is the bacteria involved in acetic acid production. All the bacteria listed, including sulfate reducing bacteria and all the other genus that produce acetic acid, and the metabolic pathway that they use to break it down to make acetic acid. So when the bacteria break it down, the complex carbohydrate, and produce acidogenesis process, they produce hydrogen, right? I told you, too much hydrogen is not good. Hydrogen will inhibit propionic acid degrading bacteria, and so you need to have balance of how much hydrogen you should have. So that is called interspecies hydrogen transfer. That's what's showing here. The hydrogen is transferred from one bacterial species to another bacterial species. When bacteria produce too much hydrogen, the hydrogen consuming bacteria are going to utilize this hydrogen. So you have this harmony of hydrogen in your digester, so you don't upset the whole system. Okay, so we have hydrogen produced during acetogenesis. The methanogenesis bacteria, methane producing bacteria, take the hydrogen and transfer the hydrogen between these two groups, and that is called interspecies hydrogen transfer process. So the last step is methanogenic process phase, and we talked about two group, acidogenic methanogen and hydrogenotrophic methanogen. The chemical reaction for each one of them, how they transfer, and biochemical a delta G value for each reaction is given there, and the species that can carry out most of the methanogenic bacteria can carry out this. Okay, this is more biochemical reaction for each type of methanogenic conversion to methane listed here. Okay. And this is more detailed than you need. This is what's happening when they break it down to methane biochemically. You need to have enzymes, coenzymes, and convert your substrate to methane and carbon dioxide. This is what's happening inside the bacteria that convert acetate to methane, convert hydrogen CO to methane, and that's a process involved here. So biochemical reactions and everything you need for bacteria to do that, cofactor, coenzyme, enzyme, genes that turned on to produce them. So a lot of information in here. Hopefully you could use it when you do your research. What are the methanogens? There are lots and lots of methanogens listed here. There are a lot of many different species. This morning I showed you two, methanosayeda and methanosacina, but there is a lot more than that in methanogenic group. Okay? So these are all listed here. Okay? So let's look at process parameters. Same thing we talked about: temperature, pH, alkalinity, trace element, redox potential, carbon-nitrogen ratio, and what is preferred in hydrolysis process, what is preferred in methanogenic process is listed. So it's totally different requirement. Okay, that's why sometimes they use two-stage anaerobic reactor. One stage to give this perfect condition for hydrolysis acidogenesis bacteria, and then the methanogenous bacteria is in a different reactor. They call two-stage reactor. But anaerobic digester is in a kind of a range, so it balances out both reactors. So individually, if you want hydrolysis acidogenesis to work at the maximum level, because your end product you want only fatty acid, you don't want methane, and you got to create that optimum condition, temperature, pH, listed for that reaction. But your end product is methane, you have to keep that condition. But if you want to keep it both in one reactor, you give a range, so you satisfy both group in one reactor. Okay? So this is available. So if you want your end product to be only fatty acid, you just prefer that bacterial dominance in your system. Okay? And resident time, how long it takes for bacteria to multiply. If you look at E. coli can double every 20 minutes as the fastest doubling time. Okay? If you look at methanogenic bacteria, it takes 14 days to multiply, right? So it varies depending on the bacterial species. Your doubling time is different. Okay? The anaerobes are very slow growers compared to facultative and aerobic bacteria. So that's to give you a dose for you for a doubling time for you for different bacteria, an example of how much time it needs for bacteria to multiply in your digester. So the efficient hydrolysis is, in order to have 100% maximum hydrolysis, you got to have these. You got to have the substrate you put in should be accessible to bacteria, right? So that means you got to break it down to fine powder or make it into slurry. So the more contact bacteria has with the substrate, the more efficient it is. Okay, it's called mass transfer. The mass is transferred easily into the cell. If the mass is not transferred easily into the cell, it's not going to be more efficient. Okay, so you need to have the grinding. You have to have the pulverized material going in there, and then you have to disintegrate your substrate. And then the crystallinity part, if it is more crystal, like cellulose and has a crystalline structure, it's going to take a long time to break it down. So these are some of those problems that you have to overcome if you want to improve your hydrolytic step and acidogenic step. What about light? Light is not inhibitory to methanogen. Methanogen can grow in the presence of light, but the methanation process to make methane, it prefers dark, right? So that's why anaerobic digesters are kept in dark, because bacteria doesn't die, but methanation process is inhibited by light to making the methane process. Okay, so that's why the methane formation should therefore be take place in darkness. This is the temperature range. We talked about mesophilic and thermophilic range bacteria prefer. Most of the time we have mesophilic bacteria. In some places they use thermophilic bacteria because it's high efficiency in production of methane. There's a pH optimum. So again, it has the range. We like hydrolysis has its own range, methanogenesis has its own range, but we prefer that range to satisfy both groups, 6.7 to 7.5, and what is happening, creating alkalinity to make more ammonia, so you have buffering system. Okay. So to avoid drop in pH, you need to go and do any of these things to solve your pH problem. Right? You can stop the substrate supply for a short time, so the bacteria will catch up with digesting more fatty acid accumulation. You can increase the buffering potential, add some lime, neutralize the acidic pH, or you can dilute with addition of water. Or the worst case scenario, you can empty it out and restart, but that's not advisable, that's really bad. So in the morning we talked about microaeration. Microaeration also will take care of the high accumulation of fatty acid. So nutrients, again, you need to balance your nitrogen and phosphorus requirement, which is given here, carbon, nitrogen, phosphorus ratio, what should be, if it is pure or carbon you are calculating, or if you are calculating carbon in the form of COD, chemical oxygen demand, it's 805 to 1 ratio. And you also have the waste material that you are using and the dry matter content, and give the organic carbon composition and the CN ratio for each of them. They'll give you some example for if you are using straw as your substrate, if you are using paper as your substrate, if you are using sewage sludge as your substrate. I gave you example of what your carbon nitrogen ratio should be. Okay, so these are all already perfected out. You don't have to re-engineer this process. Okay. The other elements, you need to have a little bit of those trace elements that is important for proper enzyme function. Then if you have too much of it, you're going to provide struvite that we talked about, that pellet this morning, that is magnesium ammonium phosphate, that can precipitate out. So you need to have trace amount of all these elements inside. Those are the trace element. What do they do? Important function of those, and the concentration range, and you should not exceed the toxicity level of. So all those from chromium all the way down to selenium, and if you have toxicity like cyanide, you should avoid them in there. Okay, so this is more information, more details of how much elements should be in your system. Oxygen. So majority of acidifying bacteria are facultative. They don't worry about oxygen. They are okay in the presence of oxygen. The methanogens are obligate anaerobe, but they don't die with a small amount of oxygen, as we talked about this morning. 1% oxygen is okay. Anything more than that, methanogen will start to die out. Okay. Other optimal conditions, material concentration, the dry matter concentration in the substrate. How do you calculate the dry matter? Mass of dry matter divided by total mass. That will give you the percent of dry matter. Total organic carbon. So how do you do that? You analyze a TOC analyzer. You take your sample, put in the TOC analyzer, that burn the carbon, convert them to carbon dioxide, and that will give you how much TOC in your substrate. If it is a liquid slurry, you can measure BOD, and also you can measure COD. So these are various ways to look at concentration in your feedstock. These are the analytical tool we use. And the other nutrients, there are various forms of nitrogen. The nitrogen is in the form of ammonia, nitrate, nitrate. total Keldol nitrogen, we have organic nitrogen in the form of protein, we have total nitrogen, then phosphate in different form of phosphate, total phosphorus, you have phosphorus or like orthophosphate. So all of them are in different form out there, so you can figure out how much nitrogen you need by calculating the nitrogen in each species and you put them in there. So when you get all those things, you get your anaerobic digester working. So here's an example of whether you have a liquid slurry or you have a solid going into your anaerobic digester, how you process them. So in the two phase I gave you, top is a fluid, a liquid, and then and if you have too much solid, you have sort it out, remove the glass and metals out of it, and then you put them in the pre-treatment and then let it go into the digester. And then anaerobic digestion, all the bacteria that we talked about, biochemical reaction takes place. You get your end product of the gas on the top, and then you get your digestate at the bottom, and the digestate could be used for various use. Okay. So the process is, there's an upstream process and the digestion process and the downstream process. Upstream include your pre-treatment. If you have a lignocellulosic, you need to work out co-digestion, how much to mix with manure. Okay? So when you get all perfected out, that's how your digester look like, and schematically your digestion carried out in a digester. It could be a simple digester, or you can make it complex. All right. So the simple is better, and then you get this two end product of your biofertilizer. And 70% of your carbon goes to biogas, 30% of your carbon end up in your digestate. So everything could be used, and it could be a biorefinery process. So that's a simple digester, right? A homemade digester. You can make small amount of gas and in your backyard. Digester from home application. For home application, you can in a plastic container. Make it anaerobic by closed lid, have an influent and have an effluent, and you're going to create your gas and the top gas collection. Okay. Digester with the heating, if you are at cold places, you want to keep a digester in your mesophilic range, you got to heat with a hot water hose going around it with the heating system. Home digester underground, and common in India. And a little bit bigger digester in the village, and sometimes in China they have a cooperative digesters. They have everybody brings their waste in one cooperative bigger digester, and the gas is supplied to the houses. They produce waste. Okay. And you can have the concrete digester. You can build digester underground. That also will work. And this is a model digester we built in Indonesia, and this is a concrete digester that work for the rural areas. Okay. Then a sophisticated one in the Western countries, and they use this huge bioreactor, and it's a lot of upstream, downstream manipulation, regulation, make it really as much science as you can. This is the 500 cubic meter biogas plant, and this is the 500 kilowatt biogas plant in Germany. You can see the bigger biogas tank, and it has a digestate processing and everything in one area. And this is the 3,000 cubic meter biogas in Bora, Sweden, and so you can make it as simple as small one, as big as industrial size, depending on the need. Okay, the process is the same, the bacteria are the same. The design is really based on what is your input, how much waste coming in. Okay. All right. Next question is whether you want to do dry or wet digestion, the solid content in your anaerobic digestion. Okay. Anything 30% or more we call dry digestion, even though there is 70% water. When you have high solids, it's hard to mix your slurry. It's really, really hard mixing